Okay, so Dalton felt that or imagined that the atom was both extremely small and indivisible, that you could not break an atom. So that's like, you know, the 4-year-old playing with Legos, and he thinks, you can't break a Lego block. I've tried with my hands, I can't do it. Well, he hasn't discovered power tools yet, right? So in Dalton's day, they didn't have nuclear chemistry, the power tools, right? We now know that atoms are actually composed of smaller particles. So the atom appeared to Dalton like Lego bricks appear to us as just one piece, couldn't be divided into smaller pieces. Now we know that atoms contain smaller particles. And in the book, it goes through some of the evidence and how that was figured out. So we have evidence that we're not going to go into in this class, that the atoms are made up of even smaller particles. Those particles are called subatomic particles. The prefix sub means below or less. And so subatomic means below the atomic level, smaller than the atom. And there's 3 that we care about in chemistry. There's some more that the particle physicists care about, but we don't care about them. Electrons, protons, and neutrons. Those are the 3 subatomic particles. All atoms contain the same 3 subatomic particles, with the exception of hydrogen that doesn't have any neutrons. But we'll just ignore that. So this table contains very important information. You need to memorize the information in this table. Over here where it says 1 over 1836, we can think of that as 1 over 2,000, essentially 0. Okay, so let's talk about the proton first. The proton has the symbol P plus, or sometimes it's just P. The proton in the atom is found inside the nucleus. We'll talk about what the nucleus is in a minute. The relative charge of the proton is +1. We actually know what the charge is in coulombs, but for chemistry, all we care about is the relative charge is +1. And we give the proton a relative mass of 1. We know what the actual mass is. It's about 1.67 times 10 to the minus 24 grams. 23 zeros, 167 grams. We can't even fathom how tiny that is. So we say, well, we're just going to call it 1. Relative mass, not 1 gram, not 1 pound, just 1. And then the neutron, N0, and sometimes we just use N, that's also inside the nucleus. The neutron has a neutral charge. The proton is positive, the neutron is neutral, and the neutron is about the same size, has the same mass as a proton. So we have these 2 particles, they're inside the nucleus, they're about the same size. The difference is that one has a positive 1 charge and one has no charge at all. And then there's the electrons. So the electrons, generally E with a minus superscript, and we usually do write the minus all the time. These are located outside the nucleus. Their relative charge is -1. So they have the same magnitude of charge as the proton, but it's opposite in sign. And then their mass is about 1 over 1836, about 1/2000th of the mass of a proton or a neutron. Essentially, that's 0, right? If you're carrying a load that's 1 ton, right? That's 2,000 pounds. And you throw something on there that weighs a pound, does that really affect the mass at all? It's just so small, it just isn't significant, right? So you need to memorize this information. Any questions? So, the nuclear model of the atom. This is what we currently use. There were other models before this. So in the nuclear model, the nucleus is the extremely dense central core within the atom. So the nucleus is the center of the atom, and that's where all the protons and the neutrons are. The protons and the neutrons are the particles that have mass, and then the electrons, which essentially have no mass, because they're so much smaller than even these other tiny particles, those are just kind of scattered about. So here's the nucleus with its protons and neutrons, and it's right there, that little dot in the center. And then the electrons, which are much smaller, are taking up this huge space. You ever notice that some people tend to just take up a lot of space? Get on the bus with them, or you sit next to them in class, and they just got stuff everywhere, right? And then some people are just, they're very compact. Has nothing to do with their physical size, but they just don't take up a lot of space. These electrons are all over the place. They are occupying a large amount of space. The nucleus is the protons and the neutrons. This gives us an idea of the size here. The radius of the nucleus is about 10 to the minus 14 meters. And the radius of the atom itself is about 10 to the minus 10 meters. 10 to the 4 difference. 10,000 times. So this is 10,000 times bigger than that little piece on the inside. It's hard to just think about those numbers. So let's relate these things to things that we understand. So the nucleus is very small, but it has about 99.9% of the mass, because those electrons do have mass, but they're so tiny that they just don't matter that much. So if a proton or a neutron was the size of a baseball, an electron would be the size of a grain of rice. Really, really tiny. It would take about 2,000 of these to make up the mass of this baseball. So that's how tiny the electrons are. How small is the nucleus relative to the atom itself? Well, if the entire atom was the size of a football stadium, right? Here's a football stadium. The nucleus would be the size of a marble. So put a marble on the 50-yard line. That's the nucleus, where 99.9% of the mass is, and the rest of the football stadium has a few stinking electrons zipping around. And because this marble is smaller than a baseball, those electrons are smaller than grains of rice. Atoms are mostly empty space. Right? If this is true, atoms are mostly empty space. Why is this desk solid? Why can't I just put my hand through the desk? It's mostly empty space, isn't it? There's forces of attraction holding things together. And there's forces of attraction holding my empty space atoms in my hand together, and so it's not, we can't just pass matter through other matter. But matter is mostly empty space. Here's another one to hurt your brain. So that tiny, tiny nucleus, that's where all the mass is. It's incredibly dense. The density is 10 to the 13 to 10 to the 14 grams per cubic centimeter. That's this number. That's a really, really big number. The density of lead, 11 grams per cubic centimeter. Lead's heavy stuff, right? If you had a matchbox, just one of those little matchbox, full of nuclei, not the electrons, just the nuclei, it would weigh over 2.5 billion tons.